This tutorial is going to go over a covariance matrix filtering run for component subtraction. Covariance matrix filtering option must be specified to perform component subtraction, so it's an option in one of the pop-up windows. PCA score plots are either 2D or 3D, depending on whether you specify 2 dimensions or greater than 2 dimensions. The outputs for a CMF run are decorrelated data, denoised data, decorrelated and denoised data, and then the Lodoit-Wolff shrinkage covariance matrix. Now, one of the things about regression is that some people, especially students, don't really know a lot of the utility of residuals in regression analysis. Take, for example, systolic blood pressure, which I have denoted here as SBP, and a predictor variable such as age. And if you regress systolic blood pressure on age, you can then estimate the residuals, predict the y-hats, predict the systolic blood pressure from the regression on age. And then because there's a high correlation between age and systolic blood pressure, so then once you get the predicted y-hats, subtract that from the observed y's for each observation, and those are the residuals. Now if you pull back the residuals, you can use those in future analyses because residuals represent the systolic blood pressure with the effect of age removed. So regressing a dependent variable on predictor variables and then estimating the residuals entails that those residuals then are adjusted by the effects of the predictors. So you'd also want to go through the predictors used in a case like that or a scenario like that and determine which ones are significant, and then likely come back as a second regression and then use the significant predictors. And then many students don't know that you can regress on predictors and then what I call pull back the residuals or estimate the residuals, and then use those residuals in future analysis. So I think, using what you have and exploiting some of the nuances, the subtle nuances of outputs from multiple linear regression can be quite powerful if you know how to do it. Here I show in terms of statistical notation regressing y, which is an n by 1 vector on a constant term, a vector of 1s, and then the vector of age, it's an n by 2. And then the regression coefficient vector is 2 by 1, obviously because 1 is the constant term and 1 is the coefficient for age. Then you get the residuals, which is e, a vector e, it's an n by 1. And then you assume that this residual vector is a y that's age adjusted. So the whole process essentially regresses some target output or outcome on a set of predictors and then assumes that the residuals are these original predictors with the effects of the predictors removed out of them. So that's the assumption here, is that you make this assumption. So it is a stretch, but this residual is the dependent variable y adjusted for age with the effect of age removed from it. Now, PCA component subtraction is a very large module in Explorer that's associated with principal components analysis and also covariance matrix filtering, CMF. So the first output of a CMF run in Explorer involves regressing. You would first run PCA on a data matrix and then regress X, the data that were used for PCA, on the first principal component here. So now instead of a vector y, you're taking your data that's a data matrix with dimensions n by p. So there are p variables, not just one. So it's X now. You ran principal components on this X data matrix, and then now you're regressing X on the first principal component which gathers the majority of the correlation among the predictors, including a constant term. Then it's a 2 by p, and then you assume that the residual is a matrix, and that's n by p. And now you assume you run PCA on the residuals then, and then you use these principal coefficients, the vectors in the principal coefficient vector. So again, quickly, you run principal components on the data matrix. Then you regress X that was used for principal components on the first principal component, which carries a lion's share of correlation among the predictors, that is X, and then pull back the residual matrix, then run PCA on the residual matrix, and then plot the two PC scores for PC1 versus PC2. And the resulting PC scores represent the original data set without strong correlation. So you've decorrelated, you've removed what's called the strong correlation. So there is other correlation, but for all practical purposes, we're calling this decorrelation because we've removed the strongest correlation. So if you had commonly the largest eigenvalue is much further and spread out as in the eigendensity distribution, and it's way out to the right with much larger positive values if there are variables that are correlated in the data set, and usually there are. That is providing you don't start with an orthogonal data set. So this is the process by which Explorer generates PC plots or PC score plots for decorrelated data. Now for denoising, Explorer will come along and run PCA on the data matrix again, and then next regress X on all the noise principal components and pull back the residual matrix E. So now you have the noise components, which are n by, there are m noise eigenvectors out of the matrix, and then you regress your original data on the noise with a constant term, a vector of ones, and then estimate the residuals, and then run principal components on these residuals, which are adjusted for noise. So noise is removed out of X. So you're regressing, same thing as the first case, with a simple linear regression and just a y vector that was regressed on age. Now you're just taking your data, which is multiple y's. You're using, by the way, you're using multivariate normal regression with multiple y-dependent variables. And the multiple y-dependent variables are formed by the X data matrix. So you regress X, you run PCA on X, and then regress X on the noise principal components. Just like if this was age, now you pull back the residuals, which are adjusted for noise. Noise is removed out of the data now, and then you run PCA on the denoised data, the principal component score, PC vector, the two vectors. So the resulting PC scores now represent a data set without noise. So you've denoised. This is also called whitening of a matrix. Now Explorer will do both, decorrelate, remove strong correlation, and then denoise by simply regressing running PCA on the original data set, then regressing the X data matrix on the constant term, the first principal component hinged to the strong correlation through all the variables or the features, and then the noise, the vectors, the principal components of all the noise eigenvalues, and then using the residuals, and then Explorer will run PCA on these residuals, and that's called decor denoise, hence DCDN. So in terms of acronyms, you have DC in the output, DN in the output for denoised, and then DCDN. And I'm not going over Ledoit-Wolff covariance matrix shrinkage here, but any of your covariance matrix shrinkage methods, and try to force a covariance matrix, with its off diagonals. It's a real square symmetric matrix for which the off diagonals reveal covariance between variables, same as the correlation matrix off diagonals reveal correlation between variables. Well, shrinkage methods try to nudge a correlation or covariance matrix towards an identity matrix. And as you know, an identity matrix, if you recall, the correlation matrix has 1 on the diagonals, and an identity matrix would be obtained if you zeroed out all the off-diagonal correlations in the upper or lower triangular. So that's what essentially most shrinkage methods do. They kind of nudge a matrix toward the identity matrix by kind of calming it down a little. Now, when you do a run, we'll do a run at the latter part of this tutorial. When you perform a run, you preferably want to start using a data set with classes in it. So in this tutorial, we're going to open the small round blue cell tumor 4-class pediatric tumor data set. And when you install Explorer in your desktop PC, this data file, the SRBCT 4-class data set, would be in Documents and then NXG Logic Explorer data files. So you'll find it there. So then you'd click on, you'd see this pop up first when you import a data set. And for data sets with class in them, following this format here, where the number of classes is specified in the upper left-hand cell, and then the class names, the 3 class names, this data set would have 3 classes. The 3 class names, feature names, there's only, as an example, 3 features here, and then a class variable, and then object names. So the SRBCT data file is in this format here. And then this is what it would look like on your desktop. So you would simply double click on SRBCT. So here you'd see the data set once it's open. There's 23 features and 23 features, 1 class feature, so there's 24, with 63 objects or pediatric tumors in the data set, split across 4 classes. And here's a close-up of the gene names. It was a gene expression data set. And then class, which is nominal. And then when the data are imported, you'd simply go to the pull-down menu of Explorer, to the Analysis tab, and then go down to Class Discovery, and then this menu will pop up, and then you'd manually select Principal Components Analysis. Then you'll have this first pop-up that's a feature selection pop-up. So step 1 would be to select all the features because we're going to use all of them. And then unselect class. We don't want class. We just want the genes that are predictive of class. We're not going to use class. And then this second pop-up window would appear, and by default it would have used the correlation matrix for PCA, and CMF would not be checked. But you check CMF, and then by default we open the SRBCT data file, which had 4 classes in it. So Explorer knows that and determines the number of classes in the class feature, and then we'll set this to 4, representing 4 dimensions, or it's a 4-class set, or 4 eigenvalues extracted from the correlation matrix. But we want to do 2D dimensional reduction and just get a 2D plot. And if you go with m greater than 2, 3D score plots will be generated. And 3D score plots can be clicked with a mouse pointer and then rotated around. We'll look at that during the run. So back to the 2-dimensional run, the 2D CMF run. Check CMF and then fill in a 2 here, and then click Apply. And then for a 2-dimensional CMF run, you will get this list of icons here for this particular run. On the top set of icons, you'll see some of the data, correlation removal. You'll see the Marchenko-Pasteur fitted eigenvalue density in a spreadsheet. And if you click on this icon, you'll see a plot of the fitted Marchenko-Pasteur density. This is the eigen density, which is fitted. And then lambda plus is used as the noise level. And then lambda minus is on the far left, where the fitted curve on the eigendensity lands at the ordinate at 0, an a y value of 0. And then the regressions that are used are in these spreadsheets. So you'll see all of the residuals, and you'll see the regressions, and you'll see the noise eigenvalues as well. Explorer will also report and show the R matrix histograms, the covariant, the R's correlation matrix histograms, the covariance matrix histograms, and then the R matrix eigenvalues in tabular notation in a spreadsheet. Then the inverse participation ratios, which are an indicator of how much each eigenvalue contributes to the variance explanation of the multivariate data set. And then for the PCA results, just straightforward PCA results for the raw correlation matrix called R raw, where R is the correlation matrix, and raw, you can see that here. The PCA output, just for the correlation matrix, would be all visible by clicking on this icon here. And a PCA output contains the correlation matrix, the eigenvalues, the eigenvectors, the loadings, and the PCs. So if you have a large number of records, you'll still have all those PCs in this spreadsheet. You'll also have a spreadsheet that contains the reduced data that you can look at, which are essentially the principal components. And then if you click on this, you'll see a 2D score plot for PCA. And if you click on this, you'll see an overlap plot or a radar plot. So then for the decorrelated data, you'll again have you're running PCA on the decorrelated data. You'll have the reduced dimension data, and then the 2D score plot and a 2D radar plot. Same thing with the denoise data. You'll have the PCA results and the denoise data. You'll have the reduced dimension data. And then a 2D score plot and radar plot. And then when you performed for decorrelated data and denoise data, when these are both applied to the data set, the same thing. The PCA results and the correlation matrix, eigenvalues, eigenvectors, loadings, and PCs, and the 2D score plot, and so on and so forth. And then for the Ledoit-Wolff shrinkage, you'll have the same output. Now, if you don't specify CMF, covariance matrix filtering, in any run for PCA, you'll have just a small number of icons in the output. So for when you specify that M is 2, or you want a 2D run, 2 dimensions, you'd only see this. But whenever M is greater than 2, now you'll have 3D score plots. You can see the score plots are all 3D. Radar plots are 2D, but the score plots are 3D. Something else I wanted to go back to. So a 2D score plot looks like this. Here's score 1 versus score 2. And you can see for the 4-class data set of pediatric tumors, you have Ewing sarcoma, Burkitt's lymphoma, neuroblastoma, and then rhabdomyosarcoma as the blue stars. And for PCA, there's very good class separation, but that's expected because these features are predictive of class. And then for a 3D run, you'd have a rotatable score plot here that could be rotated on the 3-axis X, Y, and Z. So having gone over these, we will now perform a run and do a 2D and a 3D run on the SRBCT data set. Okay, we can see that Explorer is running now, so you want to click on New Project. And then we can open or import the Excel SRBCT pediatric dataset. And in your desktop, in the NXG Logic Explorer data file folder, you'll see all the files that come with the program. So double-click on SRBCT4, denoting a 4-class problem. Here are the data: 23 features, 1 class feature, so 24 total, 63 objects. Now let's run a covariance matrix filter run, and we'll go to class discovery and then to principal components analysis and select that. Select all features, unselect class, and then apply. And let's specify 2 dimensions here, and also click on covariance matrix filter run. So CMF run has to be checked. We don't need to do anything with these settings here. Click on apply. And the run is already over, and we can see, let's start clicking on some of these icons to see what is involved with this particular run. Okay, so here you have the sample names, and you have all the Y values that are assumed. It's really the X data matrix. So this is the data matrix here with 23 columns, 23 variables, 23 features, and 63 rows. And then they are regressed. We're calling them Y now. We're regressing them on the constant term and then just PC1, because PCA was already run on the data on this data set, and we extracted the first principal component. Now we're regressing all of the Y columns onto, so it's multivariate normal regression. We're regressing them all onto the constant term and PC1, and then here are the residuals that we get back. So there's 23 of them. And now these residuals are what we run PCA on for all of the next analyses. Okay, let's look at the Marchenko-Pasteur fitted eigendensity of the correlation matrix. So if we want, we can see that lambda plus, which is the eigenvalue cutoff, below which eigenvalues are considered to be noise, and above which all eigenvalues are considered to be signal, we can see that as we go through here, we can highlight, we can select lambda, or the eigenvalue, and then this will make a plot, and this just only goes up to about 2.57. So we'll go down to this higher eigenvalue, and then insert chart XY scatter plot. And so you see here, we can actually just click on a figure in one of the icons. Here is the fitted Marchenko-Pasteur eigendensity of the correlation matrix, for which when the fitted curve intersects with 0, this is the threshold lambda plus, below which these eigenvalues are considered noise, and any eigenvalues above are considered signal. So there are more out here. And then as it drops off, but we're not concerned. Anything less than lambda plus here, which is 1.317, is considered, anything less, any eigenvalues less than that are considered noise. So let's look at this fit. Let's click on the fit icon, and you can see the same thing here. So here's the 1.37s. So we know that's 1.3, let me just check this again, 1.317, right. And if here are the other regressions that are used. So here's denoising. Now before we even get this far, I want to go to the PCA output for, or actually our matrix eigenvalues. Now, here's the raw correlation matrix eigenvalues, and let's look at these. So we know that below an eigenvalue of 1.317, any eigenvalues are considered noise. So these are signal, and then this is considered noise. So eigenvalues 5 through 23 in this 23 feature data correlation matrix are considered to be noise. So the principal components, after the first initial PCA run, the principal components 5 through 23 are considered noise. So when we run the denoising analysis, we'll regress all of the 23 variables onto PCs 5 through 23, and we'll see that. So let's go through this, and now let's go directly to that fit of the noise, the regression data for noise. So here's the 23 y variables that are regressed on the vector of 1s, the constant term, and then PCs 5 through 23 out here, and then the 23 regression residuals here. These are all the residuals here. So MP means noise. So as you can see, there are 4 signal eigenvalues, and eigenvalues 5 or eigenvectors or principal components 5 through 23 are considered noise in this noise regression, and then the residuals are used as a PCAs run on the residuals that are pulled back from regressing the dependent variables, the 23 features, onto the noise PCs. In the R matrix histograms, there's 100 bins here, and all of the correlation values were from the minimum to the maximum found were dropped into a histogram bin. So if you wanted to plot this, you'd see these are the correlation coefficients now. If you wanted to just make a histogram of that, you just insert, and there you are. So it's a little bit noisy because there's 100 bins and there's 63 data points. Okay, so 4 signal eigenvalues and the remainder of noise eigenvalues. And now we can look at, here's the PCA output for the raw data. The correlation matrix here, 23 by 23. The 2, we requested 2 dimensions, so we only get 2 eigenvectors. 2 eigenvalues, here are the top 2 eigenvalues. The loadings of the original variables and the principal components, 1 and 2. These are correlation coefficients. And then the PC scores, so there will be 63 of them. Now these are standard normal distributed, mean 0, standard deviation 1. And then they're unstandardized, and then they're standardized. Standardized are a little bit tighter, unstandardized are a little bit wider. So if you think of the standard normal distribution, for which maybe the quantiles they drop down in frequency near about 3 or 4. Unstandardized principal components score values can go out to maybe 7 or 8 or so. So they're not really, they're wider than a purely standard normal distribution. So now if you click on R raw, again, remember R raw means R is the correlation and raw means it's the raw correlation matrix. So if you click on that, you'll see 2 dimensions, D1, D2, and these are the PC scores. Now when you plot these, we can just plot these here, insert, just use a scatter plot. Here you see a 2 by 2 plot of PC1 versus PC2. And that's exactly what you'll see when you click on the score plot for the raw correlation matrix. Here they are. So PC1 versus PC2. Very good cluster separation. You can see the Ewing sarcoma, Burkitt's lymphoma, neuroblastoma, and rhabdomyosarcoma all have very good cluster clearance after PCA because these features are highly predictive of class. So there's very good class separability. Here's a radar plot where you can look at overlap from the center, and you can see that for class 4 it's spread out a little bit more. But PCA is really not, it's not that bad, but that it only looks spread out because it works from the center of polar coordinates. So if you want to go through, here's the score plot for decorrelation, regressing the data onto the principal component, the first principal component, which is strong correlation. So removing widespread correlation in these data set results in this 2D score plot. Same thing if you look at the denoise score plot. So when it's denoised, some of these look a little bit tighter. Certainly the center, the fourth class rhabdomyosarcoma objects are seem a little bit tighter, but the Ewing sarcoma seems a little bit tighter. I want to go back to the raw 2D. Yeah, there's maybe a little bit more spread. Denoising looks like it tightened things up a little bit, but there's not good. You lose a little bit of class separability there. Now, when you decorrelate and denoise, you get this, and that's not really bad. So both decorrelation and denoising tend to tighten things up. Let's look at Burkitt's lymphoma, see how tight these yellow-colored objects are in the raw. Well, they're still tight, and then when you decorrelate, they're tight. This is not a bad plot. And then when you apply both decorrelation and denoising, you see the same pretty good class separation. So depending on the data, these results for these four these covariance matrix filter methods can give widely differing results depending on the data set. You just need to run these on different data sets to find out how decorrelation, how denoising, and how both decorrelation and denoising on the data set results in PCA scores. So essentially we're coming along and running PCA on data sets after they've been decorrelated, denoised, and then both. So this is what you get. I'm not going to really cover Ledoit-Wolff, but if you look at Ledoit-Wolff, it really wasn't too bad. But if you go back to the eigenvalues for the correlation matrix, you can see that Ledoit-Wolff, the largest eigenvalue is a little bit smaller. And then you compared to, there is somewhat of a difference. It's a little bit larger, so you can see that it moves it out a little bit more. It moves correlation out this way. That's because the Ledoit-Wolff or any other covariance shrinkage method, by and large, will tend to nudge a covariance matrix or correlation matrix in toward the identity matrix. So you know that the identity matrix has all ones in the diagonal, and all of the off-diagonal elements in the upper triangular and lower triangular are 0. Well, shrinkage methods tend to calm down. They tend to tone down off-diagonals in covariance and correlation matrices. And you can see that it's pushing out the values here. The eigenvalues are kind of pushed out here. So it's not as high here as 4.5 versus a little bit under 4. So it kind of extends out here. Okay, so that's it for a covariance matrix filter run with NXG Logic Explorer version 22. We covered the correlation matrix. We covered regression of the data onto the principal component for decorrelation. We covered the regression of the data on the noise eigenvalues or principal components, essentially, for denoising. And then we talked about regressing the data on the first principal component and the noise noise PCs, and then ran PCA on all of those residual matrices to look at the scores from the data when they're decorrelated, denoised, and then both.